All right, so what did we observe? We observed that the static frictional force, Fs, it increased to some maximum. And then when that's exceeded, the object moves. Okay? So here are 3 models of friction that we're going to use throughout the semester. Okay, static friction. The static frictional force is less than or equal to mu Sn. So you notice there's a subscript on the mu as well. Because the coefficient of friction, it depends if the thing is stationary or if it's moving. Right? So Fs is less than or equal to mu Sn, and Fs max, the maximum static friction, equals mu Sn. This is the one that we use most of the time. The vast majority of the time. Okay, there's also something called kinetic friction. That's if something is moving, like this. Right? There's a kinetic frictional force between my hand and the whiteboard. So that's Fk, that equals mu k times the normal. There's something also called rolling friction. Fr equals mu Rn. I mean, have you ever ridden a bike with a flat tire? It's sort of difficult, right? Or, on the other hand, have you ever ridden your bike on Cam Highway by Sunset Beach where the road is a total disaster? It's difficult compared to where it's nice and smooth, So, now, notice these are forces, right? I don't see any vectors. Do you see any vector signs? So these are only magnitudes. So the direction is opposite to that of motion, right? Friction opposes motion. And basically it's parallel to the surface, right? These are parallel to the surface. And again, these coefficients of friction, you look it up or you determine them experimentally. Okay? Again, they depend on the material. Ice has a small coefficient of friction. Sandpaper has a large coefficient of friction. Now, these are just models. These are just approximations. But they're okay. All right? But you know that, you should think about it. Look at them. You know they're approximations because notice that these two, look at all of them. They don't even depend on the surface area. Now that's kind of weird. Just pretend this is a notebook, okay? Do you think that this friction would be the same as this friction? Nah, So again, these don't depend on the surface area. They're just approximations. For some objects like rubber and transparency sheets, they don't even work at all right? But as far as we're concerned, physics 121, physics 220, physics 220, I don't know if we use it in physics 221, but we'll always use these. But just remember, they're only approximations, and for some materials, they don't even work at all. All right? Now, what we want to do now is, I guess I'm going to use that thing again. Okay, we want to figure out a relationship between Fs and Fk. Okay? And you all know this from your experience. So this is what I'm going to show you is nothing new. Okay, so let's say you have a box on the floor or on the table or something like that, right? Sometimes it's hard maybe to get it moving. But once it's moving, not so hard, right? And so that's true, generally, And so what we're saying is that generally speaking, it's once you get it moving, it's easy. It's easier when it's moving than it was to get it moving. So Fk is usually less than Fs max. Try it. So move some box on the floor or something like that. It might be hard to get it going, but once you get it going, it's not so bad. So that's generally true. Fk less than Fs max. Okay, now let's talk a little about these coefficients of friction. Why do you suppose train wheels are made out of steel and not rubber? Cars are rubber, right? Why do you suppose train wheels are made out of steel and not rubber? Well, it's sort of obvious, right? I hope. There's probably, there's probably less rolling friction with steel than there is with rubber. Okay. So this is a table in the book, coefficients of friction. So you see there's static friction, kinetic friction, rolling friction. So look at, okay, we're talking about rolling, right? So materials, rubber on concrete. So this is like a car, right? A car tire, rubber on concrete. And there's steel on steel, dry. So rubber on concrete, coefficient of friction 0.02, pretty small, right? But look at it, steel on steel, 0.002. So, if you have a train going at a level, you don't want to have a lot of friction because then you waste a lot of energy. And you can see some of these other ones, right? Steel on steel lubricated. Look at steel on steel dry, right? And then if you lubricate it, much, much less, right? Compared to that. Wood on wood, kind of a lot. No kidding. Wood on snow, much less. And ice on ice, pretty small, right? Okay, now here's a question for you. So, sometimes trains have to go up an incline, like let's say a hill or a mountain, right? Now, think about it, you have the locomotive pulling all those train cars. So, there's a lot of weight, gravity's pulling down, but yet this train is going up. Well, how in the world do they have enough friction between the tracks and the wheels to keep that train from sliding down the hill or sliding down the mountain? How does that work? And this is kind of a funny thing. Talk about high technology. So look at a train. So here's a track, here's the train wheel, right? Believe it or not, this thing is filled with sand. And when they need a little increase in their friction, they release this and it just dumps sand on the track. So they increase the friction. That's how they do it. Maybe they have more high-tech stuff, but that's how they do it. So it's going to be interesting. So why do racing cyclists pump up their tires every day before a race? Well, because you want to get the tire as hard as possible, because then you reduce the rolling friction. This is ridiculous, right? But that's okay. You don't pump a tire like that, but it's okay. All right, now the rest of the time, what we're going to do is, so these are exercises that I want you to do by yourself first. I mean, if you have another person you work with, you do it by yourself and then you check with your friend. But please, I know I say this all the time, make sure you do it first and then look at what I did. I mean, this is the whole point of learning how to draw force diagrams. You're not going to learn just by watching me. You've got to do it by yourself. Okay? So, here you go. A jet is flying with a constant speed. Oh my gosh, constant speed. I'd underline that, right? Along a straight line, another underline or circle, at an angle of 30 degrees above the horizontal. The plane has a weight of whatever. The engines provide a thrust, or they use uppercase. We usually use uppercase T for tension, but whatever. In addition, there's a lift force and an air resistance force. So I want you to find L and R. So again, this is one of these questions where all we're doing in this chapter is drawing the force diagram. In the future chapter, we're going to solve it. So make sure on your paper, you draw the force diagram, but save a bunch of room underneath for that future chapter. Now they're very nice to us. It says that the lift force L is perpendicular to the jet's velocity. Okay, so we want to draw the force diagram, and then this is a critically important question. You'll see why in the future chapter. Is this equilibrium or non-equilibrium? Wait a second, what's that mean? Equilibrium means that the sum of the forces is 0. Non-equilibrium means that the sum of the forces is not 0. Another way of saying that, equilibrium, acceleration is 0. Non-equilibrium, acceleration is not 0. Okay? So draw the thing and answer the question. So pause the video and do that, please. Okay, so what are the forces? So weight, down, the thrust in the direction of the velocity, the lift perpendicular to the velocity, and the resistance is always opposite to the velocity. So there you go. All right, now by the way, I don't think it's worthwhile being super picky about the magnitudes of these vectors. You know, I mean, if I was really super careful, you know, I'd make sure that this component here equals that component there, and you know, I'd get all crazy about it. It's not worth it. Just draw the vectors. Don't worry about the magnitude, right? We'll worry about when we do the equations, we'll worry about the magnitude. Just get the vectors drawn, you know? Just draw the forces, that's good enough. Okay, so here's the ground, or the horizontal, I guess. Okay, here's the airplane. The thrust is in the direction of the velocity. Friction always opposes it, right? The R, what's R stand for? It's the air resistance, right? Air resistance. Weight always points straight down to the center of the earth. And it said that L is perpendicular to the velocity. Okay, that's your force diagram. You have to know how to do that. So important. We had a former student a couple, I don't know, 5 or 6 years ago. She was in grad school, and she was taking some kind of, it wasn't a physics class, it was something else, and she wrote me an email about this. And she was stuck on some problem, and she remembered Brother Weber saying, when in doubt, draw a force diagram. So she did it, and she solved the problem. So yay, force diagram is really important. Okay, so that's the force diagram. You gotta know how to do that. And constant speed, straight line. As soon as you see that, constant speed, straight line, acceleration is 0, equilibrium, bingo. And this is crucial to answer this question correctly. And you'll see why soon enough. Okay, next one. Okay, a block of mass M is held motionless by a rope on a frictionless inclined plane. You're going to love that. When you see that word frictionless, you jump for joy. Okay? All right, so the rope is holding that block in place. Then you cut the rope. Oh, you didn't see that, right? There was another slide. Then you cut the rope. Right? Well, if you cut the rope, there's no longer any tension, right? You cut the rope. Find the block's acceleration. Okay, so draw the diagram and answer the question. Okay, so pause the video and do it. All right, so now we're back. Okay, so what are the forces on it? Well, I mean, there's always weight, right? H equals mg. All right? And, you know, it's on a surface, so there's always going to be the normal force. I mean, right? Now, look at it. There's no friction, hallelujah. The rope is busted, so there's no tension, so this is it. Just two forces, the weight and the normal force. That's it. So here's the force diagram. So the weight always points towards the center of the earth, so it's always straight down. The normal force, okay, normal means perpendicular. So here's the surface. The normal force is perpendicular to the surface, you know. Now, what's the direction of the net force? Down, right? I mean, here's an easy way to think about it. Okay, so what you can do to see this easily is resolve this weight vector into a piece like that and a piece like that. All right, and so, you know, this is a horrible diagram. It's totally wrong. I don't care. There. All right, so there's no acceleration this way, right? So this piece has to have the same magnitude as this piece. So what's left? The only thing that's left is this piece, so that means that accelerates down the ramp, right? So the F net is down the ramp, and you know that from your experience, right? You know, I mean, You let the thing go, it's going to accelerate down. No kidding. Okay. And again, you'll figure this out. Oh, you don't have to. All right. Okay, so that is, let's see. I'm going to skip that, skip that. Ah, here's a good one. Oh, yeah, here's a good one. A block of mass M1, so now we have two objects, rests upon a rough incline at its angle of 30 degrees. A massless cord connected. Oh yeah, something important. A massless cord is connected from this block over a massless and frictionless pulley to another block of mass M2. Until we get to the last chapter of this semester, we're always going to assume we have massless springs and massless pulleys. Now that's ridiculous. What's a massless spring and massless pulley? What they really mean is that the mass of the spring is negligible compared to the mass of the objects. So here, the object's 2.6 kilograms, 2.2 kilograms. So, you can have a fishing line, for example. What's the mass of fishing line compared to 2 kilograms? It's nothing, So that's a good approximation. And like a pulley, I should have brought it, but I forgot. So we have these pulleys in lab. They're just made out of plastic, and they weigh almost nothing. And if you just, spin them, just hold it there, they just keep spinning, like for minutes. You just come on, hurry up and stop, But, they just keep on spinning. So they're basically, they're not completely frictionless, but almost. And again, the mass is nothing compared to these things. So until we get to the last chapter, we're always going to assume massless, frictionless pulley, massless rope. And you'll see, it just makes life easy. When we get to the last chapter, we're not going to assume that anymore, and life is going to get difficult. Here's the reason why it's nice. Whenever you have a massless and frictionless pulley with massless ropes, this magnitude of the tension equals that magnitude of the tension. So it's nice. When we get rid of those approximations, this tension is not equal to that tension, which is a mess, Okay, so how many objects do we have? 2. So how many force diagrams do you have to draw? 2. Okay, so draw your force diagrams. Now, one thing you got to be careful of, and I see this all the time. So beginning physics students, they forget that this mass is different from that mass. So they just forget the subscripts. And then like later on when they're doing their math, they just start canceling masses. And you can't, because this one is different than that one. So all I'm saying is, always include the little subscripts. This is M1, it's not M. It's M1, this is M2. Okay? So draw the force diagrams and answer the question. All right, let's discuss it. So what's the only force? What are the forces acting on M1? Normal, weight, tension. What are the forces acting on M2? Weight, tension. How come there's no normal force? Well, because it's not sitting on a surface, right? There's no surface, So all right, so normal, weight, tension, weight. Oops, what happened there? Okay, so here you go. Now, yeah, this is so they're initially at rest. How long does it take for the block to reach the ground? So it's going to go like this, right? Okay. So this is going to be moving along the surface, so it's going to be kinetic friction. Okay, so like what we just said, right? Tension, normal, weight. I think I forgot to say friction. Friction. There's kinetic friction. Again, the thing's moving this way, so the friction is always opposite to the motion, so it's Fk. Look at the subscript, you got to do that. W1, which is equal to M1G. The second one, just tension and weight. Subscript. Okay? Now, this thing is moving up, this thing is moving down. So this is accelerating this way, this is accelerating that way. See? So the net force is this way, net force is that way. Now, let me just say something that's going to help you later. What's going to be true about the magnitude of the acceleration of this guy and this guy? Well, you know, the rope doesn't stretch or do anything weird, right? So this is going to have the same acceleration magnitude as this one, right? You know? Okay, so here you have to make a decision. So, you know, we've always kind of used the Randy Knight coordinate system, right? Well, here, it's better not to, in my opinion. So let me show you what I'm saying. So what I would do for this one, okay, for that one, let me draw it real quick. Okay, what kind of coordinate system are we going to use for that? Obviously we're going to tilt it, right? So for this one, we're going to use a coordinate system like this, right? Okay. Now, in my opinion, it's and you'll see it in a future chapter, it's easiest if you always make the accelerations positive. It just makes it like easy. So for this one, you know, I'm going to use Randy Knight. Plus, plus, minus, minus. And it's going to have a positive acceleration, you know? Okay. Now, I want this one to have a positive acceleration too. How am I going to do that? So, you know, here's a force diagram, right? Tension, weight 2, right? And that's the direction of the force. So for this one, I'm going to use this coordinate system, right? So, so down is positive, and that means that this is A1, this is A2, right? But wait a second, aren't they the same acceleration? Well, of course, right? If the rope doesn't do anything weird, this acceleration is going to be the same as that acceleration. Okay? So if you just switch the coordinate system on this one, the accelerations are both the same. Now, Randy Knight doesn't do that. If you look at the book, this is what Randy Knight does. He says this coordinate system for that one, so he says A1 is positive. Then he does this for the other one. He says same old coordinate system, right? And he says this is A2, right? Which is negative, right? Negative. So he has A2 is less than 0. So then he says that they have to say A1 equals minus A2, right? That's what Randy Knight says. And just because of his choice of coordinate system. Well, I think this is complicated and wastes time. So I don't do it. I just do this. Plus, minus. So A is positive here. A is positive here. They're the same A's. So I don't have to worry about having an A1 and an A2. Just A, right? But if you don't like what I do, do it your own way. Do it Randy Knight. I don't care. This is whatever works for you, you know. But I always switch coordinate systems. I always make the accelerations positive, and therefore I don't have to have an A1 and A2. They're both the same A. To me, it's much, much easier than the way that he does it. But it's up to you. Two blocks are connected by a string. Find the acceleration of each block. Ignore the masses of the string and the pulley, like always. So know that the tensions are going to be the same. The magnitude of the tensions are going to be the same. Okay. Let's just assume that this one has a greater mass than this one, right? So it's going to go like this, you know? Okay? So draw the force diagrams and answer the question. Pause your video and do it, please. Okay. What are the only forces acting on this guy? Tension and weight, right? There's no normal, there's no friction. What are the only forces acting on this guy? Tension and weight. Now this one is accelerating that way. This one's accelerating that way. The accelerations are the same, right? Because the rope is, you know, ideal rope. It doesn't stretch or compress or do anything weird, you know? Okay? So two objects, two force diagrams. So there you go. So here's M1, M3, M2, you know, this guy. And tension, weight. And the net force is this way. M3 is going down. So tension, again, same tensions, right? because we had a good, nice pulley and the weight. But here the force is down. So again, if it were me, I would do this for M2. I would say Randy Knight all the way. I don't care about this, right? Right? And I would say, you know, so here's my force diagram. Tension, weight 2, F net, right? So that means F net is positive and A is positive, right? It's going that way. So the picture's really like this, right? That has to be greater than that, but I don't care. It's not worth worrying about when you draw the pictures. On this one, on M3, I'm making this coordinate system. And then I have tension, and then weight 3. And so the net force is down, the acceleration is down. And the way I did it, the net force is going to be positive. Acceleration is positive. So this acceleration equals that acceleration. And I don't have to have an A1 and an A2 or A2 and A3 or all this goofy stuff. All right? So that's my recommendation. Okay, oh, this is a good one. A block of mass M, 15 kilograms. That's a lot, 15 kilograms, right? Hangs by a cord of mass Mk. All right. Which, what? Yeah, whatever. Block of mass. Oh, sorry. Hangs by a cord from a knot. So the knot has mass Mk. That makes sense, right? K. Which hangs from a ceiling by means of two other cords. The cords have negligible mass. And the magnitude of the gravitational force on the knot is negligible, in other words, nothing, compared to the gravitational force on the block. So then we're going to have the gravitational force on the block, right? And we're going to say that the gravitational force on the knot is nothing compared to this, so we don't care. What are the tensions in the three cords? Oh boy. So draw the force diagrams and answer the question. So pause your video and draw the picture, please. Okay. Now notice, though, how many objects are there? Well, obviously this is an object, right? Well, what else is an object? The knot, right? Because this pulls up on it, pulls up on it, pulls down on it. So there's two objects. Okay? And I was nice. I didn't have to be nice. Put an S there. Okay, so there, all right, so the block. What's the only force acting on the block? Just the weight and this rope, right? The only thing that's acting up on this block is this cord, number 3. So the force diagram for the block is simple, you know? Just T3, tension 3, and the weight. That's all there is to it. Now, how about what are the forces acting on a knot? T1, T2, T3. Now, and again, we're ignoring the weight, right? If this thing had a large weight compared to that, we'd have T3 down and the weight down. But they said that the weight is nothing, so we don't have to worry about it. All right, so there's the block, and there's the knot. So T1, T2, T3. So you know when we solve this in a future chapter, you're going to have to resolve all these vectors and do all that trigonometry. You're going to do all that stuff you learned a long time ago. Okay, so let's review. What does not constitute a force? You have to have 2 or more objects to have a force. We talked about identifying forces acting on an object. So first you identify the object, then you identify the forces acting on the object. You better know how to drive. A beautiful free body diagram, force diagram. F equals, this is F equals ma, right? So here's basically the chapter, you know. F equals ma, right? And again, when we write F, it's really the sum of the external forces. If we're just too lazy to write it. F equals ma, which equals md v dt. That is the most important equation in all of classical physics. And then we have the three models of friction. Static friction, static means not moving. So Fs is less than or equal to Fs max, right? And then kinetic, Fk equals mu Kn. Rolling, we don't use rolling a whole lot, but that's what it is. And again, look at all three of these frictions. We have F, we have the friction equals or less than or equal to the coefficient of friction, the mu times the normal, right? They all depend on the normal. And again, usually Fk is less than Fs max. And I'm not going to do it now, but you should watch this video and just watch like the first half. You can skip the part about the engines. This is just a nice little video. And that's it. Thank you very much.